now we're going to be moving on to impact. The first speaker for this section is Silas, presenting about timely clinical diagnosis.
Thank you very much for joining, everyone. I'm Silas. I'm quite new to the lab, I would say. So this was kind of the first project I did with Mihaela, which was done as part of my medical degree, essentially, where I had a research block, and I've now joined the lab basically on a part-time basis alongside the final stretch of my degree. On a machine learning researcher, I think my primary role in the lab is kind of to ensure that what happens kind of in the machine learning side matches with what is kind of what I see or what others have seen at the hospital, because I have a background in computer engineering and am now kind of in the final stages of the medical degree. So I think I'm usually quite well suited to kind of mediate between the two parties to kind of try to kind of match what's technologically possible, what is kind of clinically needed. And this project is kind of on these fronts, because it's kind of trying to tackle essentially the issue of why so many of the kind of medical diagnosis machine learning projects that we see published never actually make it to the clinic. The reason we care so much about these kind of diagnosis tools is because actually early diagnosis makes a huge difference for many, many diseases, including cancers, where quite often if you catch a cancer at a very, very early stage, um, and you can still like surgically operate it, it hasn't spread yet or something, the survival chances are quite good, versus if the cancer then progresses to a more advanced stage where it has spread, then survival rapidly goes down. So there's a big need kind of clinically speaking to save money and improve patient outcomes, to have models essentially that for a variety of diagnoses can almost like predict risk for patients, maybe like help the clinicians essentially in this diagnosis process, because a lot of times as a clinician, you don't really have the time to continually assess a patient. The first time you assess the patient is kind of when they start presenting with symptoms, which quite often means for many diseases that you're already at a quite an advanced stage, especially for things like if you think about some of these like more silent killers, quote unquote, like many cardiovascular diseases will go like asymptomatic for many, many years and progress before then something happens. And by the time it happens, it's almost like too late to go back. Versus lifestyle interventions or pharmacological interventions earlier down the line would have been very, very relevant. Um, Another issue that's actually persisting in the clinics is that a lot of times the test selection is quite subjective at the level of the clinician. Well, quite often this is necessary. As a clinician, you are trained to judge basically what is being needed and what not. What is being seen in the clinics is right now that there's a massive over-ordering, with like almost half of the tests that are being ordered by clinicians are actually not really needed when you evaluated it afterwards. In the last few decades, with the kind of introduction of evidence-based medicines, there have been huge progresses by standardizing treatment, but it's still quite often that expensive tests are just simply not ordered due to cost constraints. And there's also kind of a problem with population level guidelines that they sometimes fail at an individual patient. So having some sort of mechanism to sometimes maybe flag individual patients that may benefit from certain extra tests would be useful. Right now, this is left at the discretion of usually a senior clinician. Um, the current machine learning technologies for kind of early classifications and stuff have, I would say, a major problem which limits kind of how they're adapted in practice, in that they don't really work the way a clinician works. So if you think about a traditional like classifier, like maybe a random forest or something, whatever it is, right, they typically assume a fairly fixed set of features that have been derived either from tests or from the like electronic health records. And then they just issue kind of a static prediction based off these features that they have learned from prior data. This is not really how like clinician diagnose patients. We'll get to that later, where it's more a sequential process where you just gather knowledge all the time and then update what you will do next, and at some point issue a kind of prediction. Another issue that is quite widespread for many of these more powerful models, including many of the transformer models such as LLMs, is that they're essentially black boxes. While some techniques like attention maps or something can give some idea of what's actually going on, it doesn't really solve any of the underlying issues, and they can still be misleading. So what we're kind of doing in this project essentially is the idea that kind of we can treat clinical diagnosis as a kind of Bayesian problem, right? Essentially, we're always trying to estimate the probability of a certain kind of diagnosis being present given a certain knowledge that is present. And this is essentially a fully Bayesian problem. There's the quite famous example, right, of whether you consider the kind of diagnostic test and what's the kind of likelihood on the right side. You can see that the patient then actually has the disease, right, given that the test is positive. And it's actually like quite dramatic that most clinicians are quite poor at judging what a positive test actually means for rare diseases. But inherently, when you think about the diagnostic process, it's a Bayesian reduction of uncertainty. As more information arrives, we can update our kind of probability of something being there given all the knowledge. This is exactly what we're visualizing here. So we start with a kind of prior belief, right? Maybe, okay, the patient has a low probability of the disease, and the true probability of the disease may be that the patient actually has the disease. And we are kind of trying to acquire more information to kind of approximate that true posterior. To do this, one method we can do, right, either in our head or with some tools, is we could think about like, well, for each test, what is kind of the likely outcome that I can get, right? So if before I measure the blood pressure, right, do I think this patient will have an elevated blood pressure or not? And then if the blood pressure is elevated, how would that kind of shift my expectation and belief of whether this patient has the diagnosis or not? And then kind of intuitively, you can think about it, right? What we're interested in is kind of the test that like is expected to shift our posterior belief the most, right? Because this is the test that is essentially most informative. If I expect my kind of likelihood of disease to drastically change if I order a certain test versus a test that, regardless of the outcome, I will assume that the patient doesn't have the disease, then the latter test is not really something that I'm interested in. And this is exactly what we're doing in this paper. So we're using a framework called Bayesian experimental design, which essentially just describes this kind of process we've done frequently is whenever we have certain problems that require, like, let's say, classification or diagnosis, we always want to acquire kind of the next piece of information that gives us the maximum information gain, or in the diagnosis scenario, essentially like the greatest reduction, essentially in diagnostic uncertainty of what's happening to approximate the kind of true belief. And this really aligns, if you look at the right side, this is kind of a schematic of what is going on. This really aligns almost with a like diagnostic reasoning between two clinicians. Mathematically speaking, all we're doing is we are approximating kind of the distribution of this kind of posterior risk as a hypothetical thing using what values we think might be plausible for kind of each test as an outcome for the patient. And then we can just calculate as simple as the like expected kind of KL divergence, which just measures essentially by how much the prior and the posterior distribution shift between each other to help us determine which of the kind of selected tests is most likely to be very informative in a certain context. Bayesian experimental design works great in many, many domains, including physics or engineering systems, where you have a good simulator of the system. The problem with the human body is that's incredibly complex, and we are still lacking even good simulators at a cell level. So one thing that we've just proposed, and this is by no means a perfect solution, but it is, as we'll see, a viable solution, is to kind of use this Bayesian experimental design in combination with an LLM. Why do we use an LLM? Well, it's kind of because it's the best thing we've got at this task. LLMs have a lot of like medical knowledge. They've ingested basically the entire medical literature there is, many patient records, like studies, and unlike some of the machine learning methods that we've discussed prior, right, that rely on very fixed inputs to produce a fixed output, LLMs are pretty good at zero-shotting to unseen tasks. So whenever I ask them with a diverse kind of problem statement or for a specific patient, what kind of test results I should get next, the LLM will always be able to at least give me an answer that is probably reasonable, as we'll see, when prompted to do so, and it can also estimate the risks. So really, ideally, we'd have this kind of simulator, and I think one of the kind of things in this kind of study is that we kind of try to motivate people to develop these kind of things. But for now, the best thing we've got is kind of a like state-of-the-art LLM that can kind of deal with this problem. The other thing our framework naturally allows, which a traditional LLM based kind of model, right? If I just prompt the LLM to ask me what's the next best test, that's kind of really like a black box. In our case, what we can do is the clinician actually can review what the LLM is kind of doing, and it's very easy to see essentially how certain um, inputs, either from my like sampled values as a potential outcome, or then as the like changes in the risk relate to each other. And it's quite easy to see whether there's like a systematic bias, for instance, in the model. So like I can review like, oh, the model predicted, right, for this patient that my creatinine would be 2.3. Is that reasonable? And then also, right, is it reasonable that this value of creatinine for this patient essentially shifts my risk estimate, let's say from 0.2 to 0.65. And this is something a clinician can do, which we've also done in the study with a couple clinicians that have looked at some representative traces, and for the large majority, I think it was almost 95% of samples that were being produced and risks that were being assigned, what the model was doing was in line with how a clinician would have assessed that result. We also then kind of just took some data sets, and what we're kind of trying to show here is that this thing actually works, and especially when we compare it to other methods that use the same LLM and the same prompts for kind of generating which kind of features we are kind of interested in, or diagnostic tests in our case, to make a classification of whether a patient has a particular disease or not. So in this case, random, I think, is quite straightforward. It just means like that we just randomly select tests, which obviously is usually not a very good baseline based on whatever is available in the data set. The global best means that the LLM decides at the start kind of a set of clinical guidelines. For every patient, I want these three tests. The implicit kind of selections means that at each dynamical step in the reasoning process, we just ask the LLM, oh, what's the next best test you want to have? Versus the ActMed, which is kind of like instead of just asking the model directly, we get the model to kind of predict what the outcome of the test might be and how that would shift our risk estimates. And we can see that kind of shifting this reasoning load from the model itself to the output space to then use a guaranteed kind of Bayesian principle for selecting the test actually improves the downstream classification accuracy. What is quite interesting is that for some of the data sets, we actually do better with some selected tests than if we just give the model access to the entire set of features that has been collected in the data set, which is partially related. This is not shown here, but essentially, the more clinical tests you give the model, there's an inherent bias in some of the LLMs that they then tend to assign higher risk scores, regardless of whether what you've added as like more clinical context actually increases the risk or whether it's just normal physiological values. Another thing that we've noticed is that actually the LLMs are very poor at generalizing. Is that when we ask the model kind of to personalize to each patient, right? When we give them what is known about the patient and then ask the model to pick the next best test, in most of the cases, actually, the model doesn't really think about what test to order, but just orders like the default, what's the next best test in a global setting. And as we have seen in the kind of prior example, using different tests for different patients does yield higher diagnostic criteria, which is something that is probably expected in clinical practice as well, as not for every person there's a single test that works well. Um, Yeah, none of this work would have been possible without the help from a lot of people. I would like to thank Mihaela in particular for trusting me with this project and for giving me access to the great resources in the lab and also the expertise from many people, including my co-author Nicolas, who is an expert in Bayesian experimental design, without whom I would have really struggled with this project. I am also indebted to Microsoft and the AI for Good Research Lab in particular, because they have provided sponsorship and Azure credits for doing this kind of research. Yeah, thank you very much.
We're going to then introduce our final speaker for today. We've got Rob talking about Synthcraft, our no-code co-pilot.
Hello everyone, my name is Rob Davis and I'm a research engineer with CCA, and I'm here to present one of the lab's latest software offerings, which is Synthcraft. One of the most important aims of AI ML researchers is always to get genuine impact in the real world. One way to do this is to put the tools themselves directly in the hands of non-programmers. How can we do this? Well, our approach in this case is through a no-code copilot, where users can interact with a copilot via natural language in exactly the same way they would do with ChatGPT. However, it is important to understand this is not simply ChatGPT. One of many crucial differences is that under the hood, we have many predefined ML statistical and analysis tools that ensure quality, consistency, and comparability of our output. But so what can copilots do? They remove coding barriers, they provide easy data analysis and exploration by leveraging tools, they can handle data quality improvement in a completely transparent manner, they provide guardrails to guide users in safe and effective application of ML and statistical tools, and they can adapt to diverse clinical questions and needs. At the Van der Schaar lab, we've built several different co-pilots to showcase their potential. Synthcraft is the topic of today's presentation, but the lab has also produced Climb for risk prediction, Climb DC for risk prediction on top of a layer of data analysis, data quality improvement and interpretability. There's Kate B for causal inference, and we also plan to develop a co-pilot specifically for digital twins as well. We've been thinking about synthetic data for a long time at the lab. In fact, our lab was the first pioneering lab to think of how to use synthetic data to empower ML research. We've published on the topic expansively over the years, produced vision papers about use, practical papers, as well as software. And back about 9 years ago, Professor Mihaela van der Schaar and the lab were thinking about this issue. They had some amazing methods that they wanted to apply to healthcare data, but healthcare data is hard to access. It's impossible for data holders to share directly with ML researchers. Private data is also heavily regulated when it comes to sharing, which can also provide a huge barrier to collaboration. And the solution that the lab pioneered in response to the problem is synthetic data. This is not just a cheap copy of the data, but generation of a genuinely new data set that matches the underlying distributions of the original data. And as the research has progressed, many more use cases have emerged. And now for me, synthetic data is underpinned by these key use cases. We have simulation. Synthetic data can be used in simulations to huge effect in work like GSIM that we've heard from Sam about this afternoon. There's augmentation for performance. Sometimes we simply don't have enough real clinical data to train reliable models. And by augmenting with high quality synthetic records, we can boost sample efficiency and improve downstream metrics, especially in low data and highly imbalanced settings. Approaches include generative models such as GANs, Bayes, normalizing flows, Bayesian networks, random forest-based methods, LLM approaches, and diffusion models. Next, we have privacy. Much of the world's most valuable data can't be shared broadly, as I discussed. Privacy-preserving synthesis lets teams collaborate without exposing individuals. Privacy-focused variants such as DPGAN, ADSGAN, PATEGAN, and PrivBase have introduced formal privacy protections. And next, the topic of fairness. First of all, we have fairness by design or inherent fairness. Instead of learning from historical biases, we can constrain a generator to produce balanced, representative populations from the start. For example, methods like decaf aim to encode fairness constraints directly into the data generation process. This reduces disparate impact before the model even starts training. But we also have augmentation for fairness or fairness by repair. Even when real data sets are biased, we can post hoc rebalance via targeted synthesis, adding records to underrepresentative subpopulations so that the final training set supports equitable performance across demographics. This is a pragmatic approach when you can't change how the data has been collected. And finally, I want to talk today about domain adaptation. Models often fail when moved across sites, hospitals, geographies, or devices. Domain adaptation-oriented synthesis, for example, approaches like radial GAN, help translate patterns from a source domain to a target domain, improving generalization without large labeled data sets on the target domain. If you'd like to hear more on the topic of synthetic data from the lab, we've run several tutorials on the topic over the years, and you can follow the QR codes on screen now to access the information, either ICML 2021 or AAAI 2023 available here. All of which brings us on to SynthCity, the lab's open source synthetic data generation and evaluation library and one-stop shop for synthetic data. SynthCity is an extensible plugin based architecture that brings all of the methods I've mentioned on the previous slide under one roof, empowering users in the use cases I've described. SynthCity's data loaders ingest tabular, time series, survival, and mixed modality datasets, and the modular structure allows your data to interface with any of the generators I've mentioned completely interchangeably. The evaluation module allows easy evaluation of the generated data. Every run can be automatically scored for utility or performance. That's downstream model accuracy and robustness, fidelity, how well the statistics are preserved, and privacy risk through a variety of different metrics. Why is the modular plugin system important? For one, speed. New methods from the literature can drop in as a single plugin with no refactoring. And in fact, you can do this at runtime. So if you generate a new plugin yourself, you can immediately start benchmarking it against all of our methods. Second, comparability. One API means apples to apples comparisons across methods and goals. And reusability. Teams can standardize on a policy compliant preset and share them across projects. The bottom line is SynthCity turns a fragmented methodological landscape into a governed, swappable, and auditable system. It allows users to move fast, collaborate safely, and consistently deliver models that are accurate, private, and fair. However, one problem remains. The clinical researchers that often have the data are often prevented from engaging with the models that they would like to exploit by the requirement to be a programmer. Our solution is Synthcraft in this case, the no-code copilot on top of SynthCity. The chatbot interface allows plain English conversation to easily understand the methods. The autopilot defaults, but with a human-in-the-loop feedback, is able to update a plan on the fly at any stage. Guardrails keep the conversation relevant to the goals of the copilot, and the data is only ever held locally, meaning you can use it with your private data. SynthCity wraps a simple chat interface around a reasoning core that can use tools, chiefly SynthCity in this case, on the user's machine. The core has two collaborating agents, a planner agent, which dynamically converts the user's goals into a step-by-step plan, and a worker agent, which executes that plan. It generates code, calls SynthCity and other related tools, runs analyses, and reports results. In practice, this means a clinician can upload a cohort. The copilot will then run descriptive statistics so that they can fully understand their data and explore it. The user then picks a SynCity plugin to generate the synthetic data in conversation with the copilot so that they can fully understand the pros and cons of any method they choose. And then the output is evaluated in terms of utility, privacy, and fidelity. The synthetic data is then also described in terms of its descriptive statistics and t-SNE plots so that the user can qualitatively explore their new data in comparison to the raw data extensively. And finally, the generated data is provided to the user. Under the hood, Synthcraft is just orchestrating SynthCity's plugin ecosystem with a learning style planner, but from the user's point of view, it's a conversation that ends with safe, useful data. That's how we widen access beyond ML engineers while preserving the quality, privacy, and fidelity we need, and how we turn synthetic data from specialist infrastructure into an everyday tool anyone can use. The power of synthetic data in each of these use cases I've described has been proved many times in the papers that introduced each of these methods, as well as in our SynthCity benchmarks paper. So I won't show too many results now. However, in Synthcraft, we show how anyone can use their own data to produce synthetic data and evaluate and compare its quality to the raw data, as well as compare between different methods. And here is one set of results I will show from our paper. I think it demonstrates how we can compare different methods of synthetic generation using the output from Synthcraft. It shows that built into Synthcraft is the ability to compare ground truth to purely synthetic data, as well as augmented data, that's the raw data plus synthetic data in one data set. And figure 8 also shows that we can achieve out of the box similar results to the raw data set for this real clinical data set. This is the NHANES epidemiology data set we're looking at here. But it also highlights that there is often a significant trade-off between performance and privacy, as the purely synthetic pay-to-GAN performs significantly worse than baseline. There is no single best generator. The trade-offs are real. If you want peak utility, ADS-GAN or CT-GAN worked best here. But if you want formal privacy, pay-to-GAN delivers that, but at an expected utility cost. Our copilot makes these trade-offs transparent, the same training recipe, same evaluation battery, and all able to be interrogated with agent-human interactions. Practically, this means we can choose the right tool for the right job and safe collaboration and sharing when needed, or maximum predictive performance when the policy allows. This slide just shows you the qualitative results that Synthcraft gives you as it allows you to explore raw and synthetic data sets. You can compare feature distributions between data sets. On the left-hand side, you see two different features, one with a raw data set, one with the synthetic data set. And so you can convince yourself that the distributions are being well represented in the synthetic data. And on the right-hand side, we see t-SNE plots that depict the data coverage, as well as exposing any artifacts of generation potentially. So 9 years on, we're still working at the frontiers of synthetic data at the VDS lab. And STEAM was accepted to NeurIPS 2025, and Synthcraft has also been developed this year. Our goal is to introduce initial versions of several different copilots, showcase what is possible, and then open source our development. We do not, however, aim to build product level copilots, as we're much more interested in research than productization. We hope that the copilots will open a new era in medicine where this new paradigm democratizes medical AI and enables every clinical researcher, regardless of technical expertise. Copilots will also allow us to easily share our solutions seamlessly with clinical colleagues worldwide, all of which with the aim of transforming medicine into a more quantitative and data-driven discipline. And thank you very much.
That brings us to the close of today's industry open house. And on behalf of Mihaela and the entire Schaar lab, I'd like to extend a heartfelt thank you to all of you for joining us today, and also for all your continued support for our research and our collaborations. And with that, thank you once again to all of the speakers and everyone for being part of today's event. And we look forward to staying connected in the future.